Hello, my name is Scott Vorthman. This afternoon, I gave an invited talk about how to use vZome specifically to make some Platonic solids and some Archimedean solids. I promised the attendees that I would record this for them to peruse at their leisure, since by policy, this group was not recording the talk. And so for your benefit, this is a little bit of a longer talk than I would normally make into a YouTube video. Um, but hopefully you'll enjoy it and you can always stop when you want. So I'm going to share my screen um, and we're going to enter the vZome application. The rest of the talk will be done from within this application. Okay, so vZome is, this version of vZome is a web application. So that means it runs in your browser. You can run this application just by visiting vzome.com/app, APP. So you can follow along with me if you like. So as a web application, we again are running in the browser, but this is also a progressive web application, which means the browser should give you some gesture that lets you install the app and it will appear in your dock or on your desktop or whatever. And then you can use it offline as well as in the browser when you have a network connection. All right, now we can't really talk about vZome without talking about ZomeTool. So what we're seeing on the screen right now is a little assembly of 4 Zome balls and 3 Zome struts. So let's talk about the ball first. It's a marvelous piece of engineering. So Zome is first and fundamentally a physical system, a plastic toy or tool for constructing objects with lots of symmetry. It's a marvelous system. So the connector ball is this essentially entirely hollow, kind of nothing but holes construction, a marvelous bit of injection molding that they completed. And there's 3 kinds of holes. There's the pentagon holes, the rectangle holes, and the triangle holes. And those reflect the symmetries of those axes. So in a pentagon hole, we can put a rectangular strut and we have twofold symmetry. Sorry, in a rectangular hole. In the triangular hole, we have threefold symmetry, and that's where the yellow struts go. And then the red struts go into the pentagon hole for fivefold symmetry. So these struts have very specific purposes. They're shape and color coded, and you can't mix them, right? You can't put a blue strut into a triangle hole and so on. The struts have very specific lengths, and they're different. So the blue strut is the longest, the red strut slightly shorter, and then the yellow strut is even shorter than that. The reason for these particular lengths will become obvious later in the talk. If you buy a ZomeTool kit, you will find that it comes with some different lengths of struts. So it comes with usually 3 lengths. So you'll find B0s and B1s. This is the nomenclature that ZomeTool uses. And you'll also find B2 struts. And let's make a B2 here. So you might notice that these lengths are related by a very interesting and well-known proportion. So the length of the B0 strut, when counted from center to center of the ball, is related to the lengths of the B1 strut, again, center to center, by the golden ratio. So the golden ratio is the larger over the smaller, roughly 1.618. Similarly, the golden ratio is the ratio of the length of B1 to B2. And that means that if you put a B1 and a B0 together, they add up to make the same thing as a B2, the same length. The same proportions hold for the red and yellow struts. Again, typical kits will include 3 lengths, B0, R0, R1, and R2, etc., and the same for yellow. So the remarkable thing about ZomeTool is its incredible expressiveness, the amazing diversity of things that you can build with such a small inventory of parts. Only 9 kinds of parts typically. Okay. And if you are interested in the physical ZomeTool, you can always click on the little info button up here and see the About screen. There's a link to the ZomeTool page here. Another thing to mention is If you're interested in vZome and you want to learn more or share models or see what other people have built, if you want to track bugs or report bugs, if you want to learn about new releases, I recommend you join our Discord server. There's a fairly thriving community there. Okay, so that's enough about Zome Tool. Zome Tool is the reason that vZome exists. vZome was originally designed as a CAD tool, as a software design application for Zome Tool. It's gone beyond that in the years since, but this is still the heart of it. All right, so now I'm going to reload the screen so you can see vZome as you would first see it when you launch it. You get the splash screen again. And what you'll see is this solid ball. So for the purposes of kind of faster rendering, vZome usually doesn't display the holes in the Zome ball. You can change that. You can go up to the shapes menu item under system and choose a bunch of different shapes. So lifelike is the one I was showing. Printable or solid is the one we're seeing now. You can also use tiny connectors if you want to emphasize the struts more. But generally, this is the best idea because you can have something that's easy to click on. Okay, so let's familiarize ourselves with the overall user interface here. I'll describe the major parts of it. So we've already seen what you do with the main view here. This is where you're going to build a model and view it. In this main view, we have two different mouse tools. So if I click on this one, I've got the camera tool, which means I can rotate with my left mouse. With my wheel mouse or scroll wheel, I can zoom in and zoom out. And if I right click and drag with my mouse, I can pan the view. So that's the camera tool. Let's talk a little bit about how this camera tool responds to the mouse drags. Because there are lots of different ways to map mouse motions to camera motions. vZome uses a particularly simple and predictable one. So if I drag from left to right, I'm simply rolling. It's as if I'm rolling the ball from the top in that direction. If I drag from bottom to top, again, it's as if my hand was rolling across the top of that ball and vice versa to come down. And in fact, this is the way it works. No matter which direction you drag, it's always going to roll as if you were rolling that ball in that direction. And importantly, this works the same way regardless of where you drag. So I can drag over here or over here on the left or anywhere. It's not the position of the mouse that matters, it's the direction of the motion. So this is what makes it very predictable. Now, many CAD tools have lots of different mouse tools, different ways to manipulate the camera. I've tried to keep it simple with vZome. And so one thing you can't do, for example, is do say a clockwise rotation or a counterclockwise rotation around the axis pointing out at the camera. But you can achieve that by taking advantage of something called precession. So it turns out if you want to rotate, let's make a strut here. If I want to rotate this blue strut, say down here, 90 degrees, that's clockwise. All I have to do is do little circles counterclockwise, and I will get there. So it's a little bit counterintuitive, but this is because rotations do not commute, right? If you do 90-degree rotations, you can see this very obviously. So we're just doing a smaller version of that when we do this little rotation. So I rotate counterclockwise, and the model moves in a clockwise fashion. So that's just a nice little tip to help you learn how to orient things the way you want. Another thing to mention is we do have the snap mode up here. So when snap is on, we'll always snap to some specific axis, and that can help a lot. For instance, when you want to look straight down a strut. I'll turn that off again. So that's the camera tool. Now let's talk about the build tool, which you've seen me use a couple times already. So let's back up a little bit, and I'll switch to build mode. Before I talk about this tool, I do want to say that on the Mac, it's an Option key. On Windows, I believe it's the Alt key. Rather than changing these with a click, you can change them momentarily while you hold down the button, while you hold down the key. So if you like to stay in build mode, but once in a while you want to be able to rotate the view, you just hold down Option and then go back to build mode when you let go of the Option key or the Alt key on Windows. Okay, so how does the build tool work? This is actually more than just build tool. We not only can we build struts, we can also select objects here by clicking on them to highlight them. And all of the tools up here in the menu are selection based, and most of the commands in the menus in the sorry, this is the toolbar. These are the menus. Most of the menu commands also are selection based. So selection is very important. But let's get back to dragging struts out. To do strut dragging, we're using these two parts of the UI. But before I talk about this part, I want to go back and talk about this part because I should have done that already. I'm going to go back to camera mode and watch what happens to this trackball if I move the main view, or what happens to the main view if I move the trackball. These two views always remain in sync with respect to the rotation of the camera. And that's very important. That lets you, first of all, even if you're in build mode, you can always use this to move the camera. That's convenient. And secondly, you really want to know how are you oriented with respect to the symmetries of the system. And that's why this trackball is decorated with these 120 triangles. There's 60 white ones and 60 gray ones. And it's also decorated with the yellow and blue and red axes. So that's to give you an idea of how the symmetry group works. The the use of the use of white versus gray triangles here is intentional. The white triangles you can think of as all right-handed, and if that's the case, then the gray triangles are all left-handed. And that means that they are mirror images of each other. So for example, if I line this ball up right here and I look at this line is really the edge of a plane. We're looking at a mirror plane edge on, and that mirror reflects, say, this white triangle into this gray triangle, right? So they're mirror images of each other. And similarly, there's a mirror plane here that does the same thing with this white and this gray. And in fact, these mirror planes reflect red into red and yellow into yellow and so forth. These mirrors are really what defines the icosahedral symmetry group. It's otherwise known as a reflection group or a Coxer group, which is a group generated by reflections. In general, vZome does not try to represent a floor or the ground or a North Pole and a South Pole, things like that. And that's because typically we're building things that have icosahedral symmetry. This is not meant to be a CAD tool for designing a house. So you won't see a sky and you won't get a North Pole and a South Pole. And so you can do any rotation. But sometimes you do want to know how you're oriented and sort of know which way is what and do some absolute orientation. And that's why the trackball has these three little black struts and the little black triangle. If I line up the black triangle so it matches this one, this is the sort of default orientation. And then in this orientation, the x-axis is going to the right, the y-axis is up in our typical sort of high school graphing paper orientation, and then the z-axis comes out of the screen toward us. And we've highlighted this triangle specifically so you can tell which is which. Okay, so now let's come back and talk about this triangle. If it's not obvious, this is a copy of any of these triangles, any of these white triangles on the trackball. And again, that's because these triangles are any of them is the fundamental region of the reflection group. It's bounded by three mirror planes. Remember, you can generate this symmetry group with any three of these reflection planes, any three of these mirrors. It need not be these three. You could replace one of those with some other one, and you'll still get the same reflection group. Okay, so the triangle here is meant to let us control what kind of struts we build when we drag. So I'm going to go back to build mode, and I'm going to start a drag, and as you'll see, I can build blue struts and red struts and yellow struts. Now, the way these struts are created as we drag is the same motion that we use for moving the camera. So going back to the way that rotation works with the mouse, instead of moving the camera, when I switch to build mode, I'm moving an invisible line. And that's going to start pointing straight out at us. And that invisible line is going to get mapped to the nearest strut that you've allowed. And we've allowed red, yellow, and blue here. You can see the little dots. And so that's the way you can think about controlling the strut. You have to imagine that trackball again. And this means that it's easy to build struts out towards you, pointing out of the screen, because going right means going right and going left means going left. If you get around the back before you let go, things are backwards. I'm moving the mouse up, the struts is going down. So it's a little bit awkward. So if you want to build a strut out in that direction, for example, it's usually best to rotate the view first and then build the strut you want. And that's another reason you want to be able to use the Option key. Okay, now if you don't want to build lots of different struts, you can put it in single mode, and then notice that we switch from yellow to blue to red, and there's only one of them allowed at a given time. And so I will only see red struts here when I scroll around. And finally, if you turn on all, it's going to turn off single. And the last thing to note about this little build direction triangle is this circle. So the last direction that I enable, and that's turn on, not turn off, will always be circled, and that's going to correspond to the length control down here. So remember, all of these directions, red, yellow, blue, and green, they're all essentially distinct. They're unrelated to each other in the sense that you can't build with a yellow length out of a red hole or out of a blue strut in the red length, etc. Simply can't do that. Blue struts have blue length, red struts have red length. And you still can control the lengths in terms of scaling up, scaling down. So for example, I can say I want to build a Y2 strut, and now I'm building Y2s. I can turn that to a Y0 and say, now I want to build Y0s. So you can always scale up and down by the golden ratio with the strut scale, the strut length control. And we have these predefined buttons that correspond to the vZome tool defined lengths. So one more thing to say about building struts, a nice little convenience. Let's suppose so I guess it looks like I'm on Y2 right now, but suppose I don't want a Y2, I actually want a shorter one. While I'm dragging with my left mouse still held down, I can, if I'm dexterous enough, I can use my another finger, my middle finger on the mouse, and actually change the length of that strut and continue the drag. And you can see that the length control on the right is adjusting as I do that. So that's just another shortcut to speed up strut building. All right. That's, I think, probably all I want to say about the general interface, and then we're going to jump into doing some specific objects, building our Platonic solids and then our Archimedean solids. So I'm going to undo everything. Actually, that bears mentioning. vZome has what we call infinite undo. So I can undo with Command Z or Control Z on Windows, one at a time. I can redo again with Command Z, Command Y or Control Y. And I can also undo everything with holding down the Option or the Alt key, and then redo everything by, again, Alt Control Y or Option Command Y on the Mac. So this means you don't have to be afraid to try things, build things, break things, whatever. You can always undo. And indeed, if you want to play around for a while and then start completely over, just undo all. And that's a lot better in general than selecting everything, say, with Command A and deleting it. Because you didn't delete the commands from the history, and the history is actually what gets stored in the file. So using undo a lot means you get more compact files, and they're faster to load. All right, so we're going to Command Y. No, we're going to do Command Z. Okay. So let's build our Platonic solids. Now, vZome obviously is, Zome tool, I should say, is obviously optimized for icosahedral symmetry. So that's going to be best for building the dodecahedron and the icosahedron, both of which have that same symmetry group. But ironically, it's a little bit clunky to build the simpler ones, the cube and the octahedron and the tetrahedron. I'm going to show you why. So I've switched to blue. I'm on single. Let's use B1. So I'm just going to say, let's imagine that I know that I need to build uh, these 6 struts in sort of the, an X, Y, and Z direction. And you noticed it was a little bit tricky because there are these other blue directions that I don't care about right now. They're just sort of getting in my way. Similarly, now that I have the vertices of my octahedron, I can start connecting them. And there's 2 ways I can do that. One is I can switch to the green struts and very carefully try to connect those up. And again, it's always easier. Oops. It's always easier if you line up so you're dragging toward yourself. But even so, you can notice that there's these other green struts that I really don't want. They're in my way. And this is because we're using icosahedral symmetry, and the object we're trying to build does not have icosahedral symmetry. It has a smaller symmetry group. So the solution for this, oh, by the way, there's another way to make those struts. I can simply select either end and use any of these join commands, which are all the same when there's only 2 balls, and I'll get my green strut that way. But all of these are the hard way to do it. So let's look at the easy way to do it. So I'm going to undo all again, and I'm going to switch my symmetry system out of icosahedral and into octahedral. All right, so you're going to see a whole bunch of things change here. Let's zoom in a bit so it's a little bit more obvious. When I switch the systems, notice that the shape of the ball in the center of the screen is changing. In icosahedral, I have pentagons. In octahedral, I have no pentagons. I have some other shapes. Whoops. Similarly, the shape of the trackball and the decoration of the trackball changes, right? And that's because we're representing the symmetry group with this figure. So obviously we're in a different group. We have to represent it differently. No more red pentagons, and instead we have blue squares. And as that changes, of course, the orbit triangle and even the length panel has to change to match. So we're simply using a completely different system to sort of render the points and line segments that we're building. Okay, so we're going to go back here to octahedral, back out a little bit, get into build mode, and let's build our struts. So I'm going to again go to single blue struts, and here, that's too short. Let's go a little bit longer. Whoops, hit a bug. Let's go a little bit longer. Here, I really can't screw up because every direction that I can make is one that I want, because there are only 6, because we're in the octahedral system. So right away, that's easier. Similarly, building with the green struts is easier because, well, we need a different length there. Guess we need, oh, I'm not going to try to, we must be using half struts for these lengths. Sorry about that. But there's an easier way yet. The thing to do here is to use the symmetry to build our figure. So to do this, I'm simply going to select the ball. I'll select the strut too. And I'm going to go up here to the toolbar. And this tool here, which you can maybe see, the icon is the same figure as what we see in the trackball. This is the octahedral symmetry tool. So I just click on that, and it's going to replicate the selected objects until we have full symmetry for those selected objects. So there's the vertices of our octahedron. Furthermore, I can still, of course, join these as I did before. But there's an easier thing to do. If I leave this thing selected, I can simply use the convex hull command, and that's under the construct menu. I want the 3D convex hull. Let's make it complete. So this will make panels and struts. And there we have our octahedron. So what it did is it ignores all of the objects on the interior. It simply looks, what are the extreme points on this figure, and essentially shrink wraps it. That's what a convex hull is. Let's do it now with struts only. So there we have our octahedron. Now, again, this is not something you can build in vZome tool because these are not vZome tool parts. But it turns out we can simply switch back. And this is kind of a tip to you that internally, vZome is storing points and line segments. It's not storing zome balls or any other kind of ball, right? These are essentially a rendering option, a style option, if you will. So you can choose to represent the same set of points and line segments using different symmetries, and that's going to dictate the way they're turned into sort of solid objects with extent that you can click on. So we never really see these line segments and points and polygons as pure geometric objects without extent, panels without thickness, etc., or struts that are just idealized lines. We'll always see them with some shape. And that's why we have the symmetry system to decide which shapes we use. So here's our octahedron. This is completely buildable with real Zome, although I think our lengths are a little wonky here for some reason. Let's build it again. No, let's not. So why isn't this an octahedron, a perfect octahedron? This actually doesn't have octahedral symmetry. And you'll say, wait a minute, Scott, of course it does. Not really. Let's focus on this ball and get it in the middle. And you'll see in this orientation, these struts have to bend kind of downward to get into to connect to the holes in the ball. And if I rotate this 90 degrees, these other struts, these green struts, are bending upward, right? So what we're seeing here, and it's kind of easy to see too, if we look right down that blue strut, that rectangle cannot be rotated 90 degrees and keep its shape, right? You can only rotate it 180 degrees, if I did that correctly. So this is reflecting the fact that icosahedral symmetry does not have 90-degree rotations like octahedral symmetry does. There are no fourfold rotations. So it's a little bit of a curious thing, although we can build an object that itself in the abstract has octahedral symmetry, if you think of it as lines and points. If you think of it as objects with shape, this does not have octahedral symmetry. And this really reflects the fact that octahedral symmetry in mathematical terms is not a subgroup of icosahedral symmetry because we don't have those fourfold rotations we can do. All right, so that's a little bit of a surprising fact for a lot of people. Let's go back to octahedral and build the next one. We're going to do the cube now. Probably thought I might want to start with the cube, but the octahedron's a little easier. So I'm going to go to yellow struts. And there are only 8 yellow struts that you can put in the ball in octahedral, and any of them will work. So let's use this one. And I'm going to select the endpoint and again use my octahedral symmetry. And once again, I'll do 3D convex hull. So there's our cube. And of course, in this symmetry, it is a perfectly symmetric cube. But if I switch back to icosahedral, this is how you would build it in real Zome. And you can see that a 90-degree, let's zoom in a little bit, a 90-degree rotation, for example, will change these narrow edge on struts to be the wide edge facing us. So that 90-degree rotation actually looks different. You can also see it with the way the yellow struts work and the look and the way the ball looks. Okay, but still very easy to build a cube if you know the tricks. Okay, so let's go back and do one more, and that is the tetrahedron. Okay, so for the tetrahedron, I'm again going to use the yellow strut. Again, it doesn't matter which one I do, although I'm going to get 2 different tetrahedra depending on my choice. Let's take this one, and I'm not going to use the octahedral tool this time. I'm going to use the tetrahedral tool, and that's going to naturally give me a total of 4 copies. And this time I'll do something a little different. We're not going to use the convex hull tool because we only have 4 balls selected. We can use this connect everything strut joining tool, and that's going to connect each ball to every other ball. And that's exactly what we need for a tetrahedron. So there's our tetrahedron. Let's switch back to the icosahedral system rather. And there's something interesting that happens with green struts in Zome tool. that makes them a little extra challenging to use. Aside from the fact, so one obvious fact, maybe not obvious, is if I do drag a strut out, notice that I have 5 different ways that I can put this green strut into the same hole. Now, obviously, I can't realistically, in real life, I can't put 5 of them into the same hole. So vZome is doing something that's not realizable there. But those 5 different struts make these things hard to use. And this is one reason you want to be able to switch to octahedral to work with green struts in most cases. Oops, I hit the wrong key, excuse me. Don't want to save. Okay, so I'm going to undo. And the other oddity about these things is to illustrate this, I'm going to select all, and I'm going to do the central inversion. So this will reflect everything through the center to the opposite point. It's the same thing actually as doing 3 orthogonal mirrors. And that gives us this stella octangula, right? This compound of 2 tetrahedra. But the interesting thing about this is if we look at these triangles, if we compare this triangle in the back with this triangle in the front, you may think, oh, they look identical. But they're not. They're actually different. One is right-handed and one is left-handed. And if you look at the way the struts enter the balls. So it doesn't matter how I rotate this, these are not the same. I can't make one look like the other. And so this is a bit of a pitfall when you're building with green struts in real vZome. You build an equilateral triangle, you build a second equilateral triangle. It's very easy to have those two things not work together. For instance, not be 2 faces of a tetrahedron because you made one right-handed and one left-handed. But fortunately, vZome has no such restriction, or rather, it's easy to circumvent it just by using the octahedral system, where everything is correct and looks the same. Okay, so we've made the first 3 Platonic solids, the smallest 3, and we've used the octahedral system to do that. But now let's build the best 2, if you will, the dodecahedron and the icosahedron. So I'm coming back to the icosahedral system. I'm going to use the yellow strut again. Again, because we're going to do symmetry, it doesn't matter which yellow strut I use. Let's use a little bit longer one. And we'll just select it. And in fact, what we're doing here is really what you would do in vZome Tool to build a dodecahedron, except you would start out by sticking yellow struts into all of the holes, all of the triangular holes of the vZome ball. And then once you're done, you would achieve this. And then you simply connect up the edges with blue struts. And there's your dodecahedron. So vZome is doing the exact same thing. It's just letting you do it a lot more quickly. So we'll make our one yellow strut. We'll do the selection there. And we don't even need to construct the symmetric scaffolding. We can just say symmetry, there's our vertices, and convex hull to get our struts. And there's our dodecahedron. So that's a dodecahedron made with B1 edges. Suppose you want it to be B2 edges. One of the tools I haven't mentioned, or 2 of the tools, are these scaling tools. So this one scales up, and this one scales down. And of course, you can go as far as you like to the point of silliness, either way. All right. So there's our dodecahedron. Let's undo that for the moment, and let's go back and make an icosahedron. So I'm going to switch to red struts for this. And let's make it a little bigger. Oops, not that big. Select our ball, apply our symmetry, and kind of do the convex hull again. And there's our icosahedron. So 20 equilateral triangles. Now there's an interesting thing that happens here with the icosahedron and the dodecahedron. So I'm going to build my dodecahedron again also in just a few clicks. And what you can notice here is that every edge of the dodecahedron intersects an edge of the icosahedron, and they intersect at right angles right in the middle. This is because these 2 objects are duals of each other. So for the duals, there's different exact ways to define it. But roughly speaking, you can say for every face of the icosahedron, every triangle, there's a vertex, a ball, for the dodecahedron, and vice versa. So for every pentagon of the dodec, there's a vertex for the icosahedron. And that means if we get the sizes right, that we'll get these two intersecting perfectly. Now, interestingly, we can build both of these with blue struts. So you might ask yourself, well, if we only need blue struts to build these, why did vZome add red and yellow struts? And really the reason is because you want to be able to build from the center, right? So the red strut constructs the center from the vertex of an icosahedron, or alternatively, it's half the diameter. So I can connect those two, right? So that's the red direction, and the distance is defined by the distance to the center. And the same is true for the yellow struts and the dodecahedron. So that's how, even before vZome, that's how Steve Baer designed the original vZome toy and his playground construction equipment building system in order to build these interesting polyhedra. All right, so now we've done all 5 Platonic solids. Let's branch out and do some Archimedean solids. And to do that, I'm going to do it a little bit differently. And we have something of a helper, a quick start for this. Not the quick start, sorry. We have symmetry starter documents. And before I jump into them, I do want to point out there's a lot of good stuff in the help menu. You can go see the vZome home. You can learn how to share vZome files online. This YouTube video, for instance, will be on the YouTube channel, the vZome YouTube channel. And there's many other useful links. For example, the Discord server, miscellaneous online documentation, etc. So do explore that. But for now, let's open up one of these starter documents that help us build with particular symmetries. So I'm going to do the one for icosahedral dodecahedral symmetry. I don't care about losing my changes. So here's our starter document. So just to make things obvious for you, it repeats this trackball model, the 120 triangles, so you know that you're looking at icosahedral symmetry. And for one of those triangles, we see the bounding mirrors. Now, these mirrors, of course, are infinite planes. They would normally go out to infinity and extend beyond these struts, beyond the triangle. But just for convenience, and so we can see everything easily, we are truncating the mirror planes just to these faces. So we have the blue mirror, the yellow mirror, and the red mirror. And the red mirror is a red mirror because it's opposite the red strut, and it's ditto for blue and yellow. So we already know what we're going to get if we say select this yellow ball at the end of the yellow strut. That's going to give us a dodecahedron. So we're not going to do that one. Similarly, the red would give us an icosahedron. But we haven't really explored what a blue strut would give us. So let's do this one. So I'm going to select it. I'll apply the icosahedral symmetry. And then I'll do the full convex hull. And we'll back up and click on the background to deselect. And we have an icosahedron. So because this is all made of regular faces, so regular pentagons and equilateral triangles, it is an Archimedean solid. Notice that there's still only one kind of ball. In all of these Archimedean figures, we're going to find that all the balls are equivalent, and that makes sense, right? We made all these vertices by using the symmetry tool once on a single starting ball. So we do expect them all to be symmetric. And in this case, although there are 2 faces, there's only one kind of edge, the boundary between a triangle and a pentagon. So, oops, I don't want to undo all. I just want to undo a couple. So let's try another one. So what are the other choices? Now we have 3 or 4 of these points that are on the mirror planes and one that's out in the middle. So let's do the ones in the mirror planes first. So let's see if we can reason out what to expect here. So this ball is lying in the red mirror, which means when we reflect this with the symmetry of the group, we're not going to get a strut here because this ball is its own reflection in that mirror. But it will reflect in the blue mirror, and it will also reflect in the yellow mirror. So we expect to get two kinds of struts where those reflections are applying. So let's see. All right. So here we have our truncated dodecahedron. And that ball was exactly located in the right place so that these two edges, the triangle decagon edge and the decagon edge, are the same length. So when we say truncated dodecahedron, we mean that we've taken a dodecahedron with red pentagon faces and we've ground down or truncated these threefold axes. So there would have been a point here where this was a pentagon, and we just ground it down just enough, just the right amount, so that these two become the right length. And that gives us an Archimedean solid because this is a regular figure. Okay, so that's one of my favorites, the truncated dodecahedron. All right, what's the next one we want to do? Let's do the sulfur colored ball here. So I'm going to apply the symmetry, do the convex hull, back up, deselect. This is a truncated icosahedron, or what you might recognize as sort of the canonical soccer ball shape, with regular pentagons and regular hexagons. Once again, we have now two kinds of edges. Remember, we used two mirrors, so we were lying in one mirror, so we used the other two for reflections. And that gives us the hexagon edge, the same length as the pentagon hexagon edge. And the length is right because of exactly where we started with this ball. So once again, another Archimedean solid. So let's do the last of these three, the lavender strut. Reflect, construct, click. And here we have now suddenly three kinds of faces. We're still only using two mirrors, but because the two mirrors we're using are at right angles, we actually get three kinds of faces. We get regular squares, regular triangles, regular pentagons. And we still have only two kinds of edges, triangle square and pentagon square. So that's the rhombicosidodecahedron. Now, interestingly, I've provided another nearby ball that looks roughly the same. It's in the same mirror plane, but it's slightly in a different location. So let's select that one and see what we get. Maybe you can guess what we're going to get here. So topologically, we have the same thing, same number of faces and vertices and edges, but what were squares are now golden rectangles. And the reason this one is provided is because this is the shape of the vZome ball. And you might ask, why did vZome tool and Paul and Mark use this rectangular face instead of the square face? Why not use an Archimedean solid? And there's a very, very good reason, and that is if you had square blue struts with square holes, then you would have the possibility of a blue strut with two balls, one on each end, that are misaligned, that are 90 degrees rotated relative to each other. And you don't want that. That violates the system. That's going to introduce all sorts of problems as you build further with those balls and struts. So they wanted to respect the symmetry of the icosahedron, which only allows twofold rotation around these axes. So the obvious thing to do is to make this a golden rectangle. And then you get actually a nice pleasing side effect that all the struts have sort of the same cross-sectional width, which is this golden ratio scale relative to the edge length. So here we have the long edge of the long edge of the rectangle is the same length as the long diameter of the pentagon and the edge of the triangle. Okay, so we've made almost all of these that we can built in with this. So let's go and figure out what happens with this interesting one in the middle. So it's going to use all three mirrors because it's not in any of the mirrors. So we expect to see three kinds of struts when this ball gets reflected to its neighbors. But there's a trick here. This ball is coming out. This ball is sort of centered, this strut, I should say, is centered in a white triangle. And if I don't reflect it such that I get one also centered in a black or gray triangle, I'm not actually going to get any reflections automatically. This tool does not do the full reflection group. It only does the rotations. Now, this didn't matter when we were using any of these others because they were all being reflected naturally because they lie in these planes, in the mirror planes. But this one doesn't lie on any mirror planes. So what happens if I apply the symmetry and connect up the convex hull? Well, what I'm going to get is an object that only has the rotational symmetries of an icosahedron. And this is a very interesting object. Pretty, nice colors. It is actually similar to a true Archimedean solid, and that's the snub dodecahedron. But in the snub dodecahedron, these triangles, these green triangles, would be regular. They'd be equilateral and look the same shape as these. You can't actually build the snub dodecahedron with vZome tool. So this is as close as, well, not as close. You can get closer in vZome. But you can't build this in vZome tool anyway because these are not red struts. Those are orange, and these are purple struts. These struts only exist in vZome or if you want to do some 3D printing. So this isn't what we were actually after. We wanted an Archimedean solid. And so what we need to do is get a reflection, right? We need, again, one of these balls to be, one of these stalks to be coming out of a black or gray rectangle or gray triangle as opposed to a white one. And I can do that very easily just by using the central symmetry. So now if I look at that one, it's coming right out of a black triangle. So now I have a sort of a right-handed vertex and a left-handed vertex. And now if I apply the symmetry, I get the nice reflection symmetric Archimedean solid. This is the great rhombicosidodecahedron. Where we had pentagons, we now have decagons. Where we had triangles, we now have hexagons. Everything is the same edge length, of course, because that's why we position it just exactly in that position. And once again, we have three, as we predicted, we have three kinds of edges: yellow, red, blue, blue, yellow. Okay. So that is probably as far as I want to go for this talk. And there's plenty more to explore. For example, you can use the other symmetry starters, cubic octahedral. You can do the cubic octahedral not in the vZome system, but using the root 2 system. And you can do tetrahedral. So we're not going to look at those today, but you're welcome to explore them. There's lots of interesting stuff happening with the tetrahedral system. You could argue that I should have made a tetrahedral alternative here. I simply haven't done it yet. There's extra complications for tetrahedral because it uses not just blue mirrors, but also green mirrors. All right, so that's it. So I hope you enjoyed this and stay tuned for more content. Thank you.